Physics 101, static equilibrium homework set. Question number 9. We have a box that's sliding down a ramp. It's stopped by a spring-loaded arm. The arm applies a force that brings it to rest, and we end up at a static equilibrium. The forces are all equal because it's not accelerating. So we've got several forces acting here. We have the arm holding it up, pushing directly to the left. We have gravity pulling it down, acting directly down. We have a frictional force going up the ramp, and we have a normal force perpendicular to the ramp surface. Those forces are going to all add up to 0. We know that this normal force is perpendicular to the ramp. We know that the frictional force, Fs, is going to be at its maximum static friction because the arm, we're asked to find the minimum force that the arm would push at, and that's going to occur when the friction is holding it up as much as it can, which is going to happen at the maximum, Fs max, maximum static friction. Then we have our arm force, and we have gravity, Fg, which is going to equal m times g. We know a little bit more. We know the angle here is going to be theta. The frictional force is going up the ramp, and the ramp is at an angle theta, so the frictional force is at an angle theta above the horizontal. And we also know that the normal force is at an angle theta from the vertical, from the up and down, just by geometry. So I'm going to draw another free body diagram here. There's our box. Doesn't look like a box, but that's what it is. We've got our normal force, Fn, at an angle theta. We have our frictional force, I'm just going to call it Fs, even though we know it's the max, Fs, just to save some space. And it's at an angle theta as well from the horizontal. We have the arm force, which we're trying to find, F arm. And we have gravitational force going straight down, Fg, which equals m times g. Sometimes when we do these problems on ramps, we'll change our coordinate plane so that it is making the ramp seem flat. But in this case, we have just as many ups and downs in this that are on our coordinate plane as we do forces that aren't. So it's just as easy to keep it as it is as it would be to change it. So there are no torques, which is nice. There's no rotation in this one, just forces to deal with. And since the forces all balance out, if we look at the y direction, the force up has to equal the force down. If the net force is 0, then the positives have to equal the negatives to add to 0. So the upward forces have to equal the downward forces. In the upward direction, I'm going to draw them in yellow, we're going to have the y component of the friction, and we're going to have the y component of the normal force. So Fs in the y direction plus Fn in the y direction, and that's going to equal the downward force, which is Fg. Static friction, Fs max, is going to equal mu s times the normal force, Fn. And since we only want the y component of it, and according to theta, that is the opposite side, that's going to equal Fsy is going to equal mu s times Fn, and since it's the opposite side, it's going to be the sine of theta. The normal force, the y component, is the adjacent compared to theta, so Fny is going to equal Fn times the cosine theta, because it's the adjacent compared to the angle. So plugging that in, for Fsy, we have mu s times Fn times the sine of theta, plus Fn times the cosine theta equals m times g. We only have one unknown, and that's the normal force. So we can find the normal force in this. We didn't know what it was before, but we can. I'm going to factor that out, so it's going to be Fn times the stuff that's left, and then divide all that stuff over to the other side. So Fn is going to equal mg divided by all the leftover stuff, which is going to be mu s times the sine of theta plus cosine theta. That's going to give us a value for Fn. Awesome. Now we're going to look at the x direction. Low in space. I might need to go to another slide, but let's look at the x direction while I still have it on this on my drawing. So in the x direction, the lefts are going to equal the rights. So force left equals force right. To the left, we have the arm, F arm, which is what we're trying to find. And to the right, the only thing we've got is the normal force component pointing to the right. So it's going to be Fn x. But Fn in the x direction, if Fn in the y direction was Fn cosine theta, Fn in the x direction is going to be Fn sine theta, because it's the opposite according to theta on our triangle. So F arm is going to equal Fn in the x direction, which is equal to Fn times the sine of theta. Well, we know what theta is, it's given the problem, and we know what the normal force is because we just solved for it. And that's how we find the force applied by the arm.